we'll talk about something that are needed to deliver the fact that from our computer, if they look at certain address, certain piece of data, they should have the same value at any given point in time. Like if you say, hey, I want to pause the time, and I look at the sequence of what's happening, how can I make sure that you can, in the end, after you resume the time, you see the same set of sequence of things, right? And this is called memory consistency. To recap quickly, let's talk about what we've been talking about multiprocessor, right? And the benefit of multiprocessor is enable more performance, and you can utilize by running multiple programs, multiple threads. And the key issues that we've already talked about are resource sharing. We talked about data coherency last Wednesday, and hopefully you pick it up to some extent, and to the point that at least you can formulate some questions about like what is going on. To the example that I gave at the end of lecture. What are we going to cover today is how to ensure data consistency. And if you take the OS class, now it's more about like, okay, you have multiple processor, multiple tasks. How can you map what to run at any given point in time? And so, as I said, we talk about consistency. This means that when you have shared data, everyone can see a Facebook post, right? If it's public. And with that example, if I'm posting something and someone's making about a lot of comments, right? The order based on time, the order that you can see the comments should be ordered based on reads and writes sequence that every single computer can see, right? For example, how many of you played Dota 2? Or any like, what's it called, MOBA? Okay, so if you play Dota 2, you know that there are 10 players, right? Basically, there are 5 on each side. And basically, you fight for the throne, right? Well, I mean, basically, if you can finish off the throne, you won, right? Regardless of what cost, you can dive the fountain, you can do whatever weird things with it. If you kill the throne, you win. Anyone here not familiar with like the part where they can have two sides hitting the throne at the same time, they're competing who finished the throne first? I forgot what it's called actually, even though I watched a lot of Dota games. But when they go all in, try to hit the throne and try to see who kill it first, right? What will happen if all 9 computers think that the Radiant killed the throne first, but that last computer somehow, the packet from every single computer where you have a data packet saying, hey, the Dire hit the throne and the HP is 0, the Radiant throne is destroyed without the Dire throne being destroyed. What will happen in that instance? What does it mean? 9 players saying the Radiant is winning and won. The Dire, there's one guy on the 10 players here that see the Dire won and the Radiant is like losing. What will happen if that's in the real match where it's like, let's say it's international final? So for those of you who never played Dota, basically there are 2 sides. One side is called Radiant, the other side is called Dire. And I'm talking about a situation where 9 players computer see that the Radiant is 1, and 1 player computer see the Dire side 1. Right? What will happen? Chaos, right? They'll be like, what the heck is going on? And this is basically means that you want to make sure these such case never happen. And in a real match, do you ever seen this happening? How many watch like hundreds of hours of Dota 2 match like me? over time, of course, not in a year. Yeah, used to. It made me feel bad. I still watch it these days. Well, not this. Yeah, I used to watch a lot more. After COVID happened, we don't have international this year, so I watch it a lot less. So, and have you ever seen that happening? The case where somehow there's a conflicting results where one computer see different. It never happened, right? The reason why this thing never happened is because of memory consistency. Every single computer in the network that are connected, especially in this case where 10 players connected to the same game, right? They should see the same sequence of things. Same sequence of things. Another example is, let's say I have two players that try to use the skill to stun the other side, right? And what happened if you got stunned? Usually you have to wait 2 seconds and you can't do anything. Okay. What if, from your computer point of view, you see that you stun the other side first, the other side see that they stun you first? Who gets to wait? Right? Again, this is memory consistency coming into play. Every single machine will see the same sequence. Will see the same sequence. Any questions so far about this high level examples? So the reason why this never happened is actually this is specified by the ISA. When we design the ISA, we think about this multiprocessor scenario, and this potentially legit can happen, right? Why is it happening? Network latency is not guaranteed to be the same, right? When you ping google.com, you see different latency. Sometimes it will take only a few microseconds. Sometimes you will have to wait a longer millisecond. Millisecond is longer than microsecond. So this variation of time it would take to write or read the data can lead to consistency problem. The ISA will determine, okay, if this thing exists, how should I manage it? How should I manage it? It allows the expected order that every single machine will see, right? On a single processor, this is simple. Von Neumann. Architecture 101. What is the von Neumann model? We covered this in the first lecture. Anyone still remember this? Anyone still remember what von Neumann model is? Yes, line by line. I was about to say, so the private answer coming to me is executing things line by line, and that's exactly what it is, right? So in a single processor, consistency is simple. Line by line by line by line. You know there's a straight line code. That is the order of where things should happen. In the data flow model, that's also pretty simple, right? If there are data dependency, the dependency determine the ordering, right? The dependency between each operation. Let's say the add produce the data for the multiply. So that dependency determine who should go first, what should happen. In the multi-core processor, typically, if you write a thread safe code, this is basically the proper guideline with the way you should write parallel programming. Thread should not update the shared data at the same time. If you're taking OPL, if you took OPL 2 semesters ago, or if you're taking parallel programming this semester, one thing I'll tell you is if you have writes, everyone else are not supposed to be able to do anything with your data. That's sequential code, right? Because that writes create the critical section. In C, in different language, there are multiple constructs that you can use to protect the critical section. Things such as logs, semaphore, or conditional variables are designed to basically protect the critical section. And And multi-core processor, when you run, say, Dota, right, it should provide this correct execution order based on this primitive. If you write the Dota 2 game, you want to make sure the case where I mentioned earlier never happened. If someone see that the thrown HP becomes 0, it should conclude the game saying, hey, the other side won the game. Regardless of that, maybe one single computer thinks otherwise, right? There has to be certain strict policy on what happens here. It's like a game of soccer or American football or things like that. There'll be a referee. The referee will tell how should we proceed through this messy situation. So basically, the hardware needs to make sure what the programmer writes, what is the true sequence, assuming, big assumption, that the programmer not know what you are doing, right? What they are doing. Anyone want to take a guess why this is a pretty big assumption in many cases? How many you malloc your array and forgot to free? At least 5 times when you are going through the system skill or file processing. Yeah, me too. So because we are human, right? We tend to make error. And even though we have a pretty well-known guideline, we do make errors. A lot of time the compiler is a tool that can help detect that. While grind is another good tool to help detect it, right? The hardware also have the ISA to kind of help, but it's just a guideline. So if you know what you're writing and if your code is correct, then it should be correct once you run it based on how you program. Okay. Hardware, one important thing that I want to tell you here is the hardware will just run based on how the programmer tells the hardware to do. Hardware is dumb. It's just a piece of thing that listen to the code you program. So whatever you command them to do, they'll do exactly just that. Right? The hardware is designed to do exactly just that. Right? It can't just go and become sentient and do its own thing. Those are the things in the movie is not as simple as what they make it seems to be. We program it this way, it will behave the way you program it. So, any questions so far before we go into this concept called sequential consistency? All right, so let's define what is sequential consistency. Anyone seen this terminology before? All right, the long pause, I assume no one's seen before, which is good, so that I can define it here. It's actually defined in this paper by Leslie Lamport. The paper is called How to Make a Multiprocessor Computer That Correctly Executes Multiprocess Program. It's published in 1979. And if you read the title alone, you will know, okay, this is going to be related to multiprocessor. It's going to be related to correctness, right? And this is basically what sequential consistency is aiming for. You run things in multiple processor and it should be correct. So the multiprocessor is sequentially consistent if the result of any execution is the same as if the operation of our processor is executed in some sequential order. Stress in some sequential order. Oops. I need my pen. So let me change it. Some sequential order. And the operation of each individual processor appeared in this order, in this sequence, specified by its program. This is called the memory ordering model that is specified by the ISA. The definition might sound a little bit convoluted, so let me use an example, right? So let's assume there are four operations, A, B, C, and D. Four operations, they can modify the memory, they can read the memory, they can be a read or a write. Any permutation of these operations can be a correct global ordering. The actual observed order depends on the implementation and the dynamic latency. So what does this mean? Let's actually draw what happened, right? So you have four requests, A, B, C, and D. Let's say you have two processors, processor 1 and processor 2, P1 and P2. They share the memory. They both share the memory. This is like multi-core CPU. What does sequential consistency mean is if processor 1 see this sequence, A, C, B, and D, is that okay? My first question is this okay so far? I have four operations and I say, okay, processor 1 C, A, C, B, D. Is this okay? By our definition. This is actually okay. The reason why this is okay is sequential consistency doesn't care about what order that you see. This might be a bug in the program, right? That say, okay, somehow A, C, B, D, you forgot to lock, so C and B can swap. What is important is processor 2 will have to see the same sequence, A, C, B, and D. They have to match. Basically, they have to see the same sequence. Anyone here want to guess why they have to see the same sequence? Anyone want to type anything on the chat? Why both processors have to see the same sequence? Yes, well, consistency, because that's what we are learning. If you translate that to a little bit more like human language, basically, the reason why is, let's say you are the programmer, right? And you're trying to figure out what's wrong here. If you look at the memory, from processor 1 point of view, you see A, C, B, and D. From processor point of view, you see A, B, C, D. Who can you trust? Right? The memory should pick one of these order, right? In reality, it should be A, C, B, and D. The same thing that processor 1 and processor 2 see. And if processor 1 C, B, D, B, C, A, what does processor 2 have to see? What is the sequence processor 2 should see if you have sequential consistency? D, B, C, A, yes. Basically, the same sequence has to be seen globally across multiple processors, right? This is the same as Dota 2 games that I mentioned earlier. All the 10 players should see whose drone die first. Otherwise, you're gonna get into the problems as to who won, right? I see that my drone died first. The other people see that the other drone HP becomes 0 first. They get destroyed first. So who won? The solution is make sure there's memory consistency. Every single processor should see the same sequence. It means the problem I mentioned earlier should never exist. Right? With that assumption, the problem I said earlier will never exist, will cease to exist. So here's the benefit. Well, all processes see the same global ordering, right? There's no correctness issue due to the process seeing different data. What does it mean? What does no correctness issue due to processes seeing different data means? It means that whatever each process see, it should be the same sequence, and that's all. Does not mean your program is bug free. Doesn't mean your program is bug free. It still means that across multiple execution of the program, different ordering can happen, right? So if you look at the sequence A, B, C, and D, right? A, B, C, D, the run number one, right? If you run it first time, you see A, B, C, and D. You run it again, you see B, A, C, D. You run it again, you see D, C, B, A. You run it again, all the processors see C, B, D, A. You run it again, all the processors see D, D, C, A. Are these possible under memory consistency? You run it 5 times, you see a totally different order. Is this possible? Is this possible? Look at my second bullet. Does it mean I run 5 times? I see totally different order. Is it still hold? Does my assumption still hold? Should I repeat the question? It is possible, yes. The reason why they are possible is because sequential consistency never talk about what happened when you run it again. If you run it again, you see different order. That's your fault as a programmer. That's not supposed to happen, right? Or unless if you design for that to happen, you need to really, really know your program well and make sure that that's okay. What are the downsides? Global ordering is a strong guarantee. Do we need global ordering? Basically, how often does critical section actually modify the shared data, right? My second question is, what modified the data between load and store? What will modify my content in the memory? Between read or write, what changed my data? If I'm reading, does my data change? Does my value change? Or is it when I'm writing? It's when I'm writing, right? So when you have a store operation instead of a load, you are modifying your data. So our idea is this. It is not an idea. It is like a proper implementation for weak consistency model. But what if we enforce global ordering only at boundary of synchronization? When I write, I want to make sure I have global ordering. This is called relaxed consistency model. The reason why they're called relaxed, well, it's not as strict, right? So here's a idea, right? Here's the explanation of the idea before I go through the example. Ordering is only important when the operation affects the shared data. What does it mean? The programmer specified a non-shared region. This is done to either memory fence, barrier, and things like that, depending on the language you're dealing with. Memory operation before the fence must complete. Memory operation after the fence must wait for the fence to complete. And the fence is completed in the program order. The downside is you have to carefully program this, and here's the example. let's say you have memory operation A, B, C, E, and then fence F, G, fence H, I, J, K, L, fence M, and N. Fence. This means it's a fence. So let's say this is my memory operation, and these are the 4 fences that I have, right? Is it okay if processor 1 observes something like this? A, B, F, C, D, E, G, H, I, J, K, L, M, N. Is this okay? Is it okay to have the F coming here? Nope. Yes. I mean, the answer is correct. Your answer is correct, champ. In the sense that F should happen after A, B, C, D, E. This means that if I see something like this, so this is not okay. If I see something like, I'm gonna just reverse everything, but still in the realm of possibility. If I see something like E, D, C, B, A, followed by G, F, followed by L, K, J, I, H, followed by N and M. Is this okay? This is actually okay because you never break a fence. Basically, when you have fence, operation should not go across the fence boundary. So if you have things like this is okay. You have things like this, followed by this is okay. If you have things like this is not okay. If you're moving from here all the way to here, this is also not okay. Don't cross the fence. And this is basically how you can program. The reason why I said as a programmer, now you have to be more careful. Why? Because you need to design where to put out the fences. The hardware just listen to your program, say, hey, put a fence here, put a fence here, put a fence here, put a fence here. It will optimize your code in a way that makes sure whatever order inside the fence I see, I don't care. I just need to make sure everything is done before the fence. You get committed before the fence. Everything that it will be done after the fence will get committed after the fence. All right. Any questions? Any question? Basically, this is it, guys, for the class. This is it for this architecture class. Anything after this are extra that I basically want to give it to you. No, anything after this are not going to be on the exam, except for let's put everything together again. All right. Do you want to take a quick break, or should I keep going? Okay, so I assume yes is it a yes for keep going or yes for a break? Okay, let's do a quick break. If you have any question about memory consistency, let me know. This is like really, really important topic in computer system. Actually, not well, it's still important in architecture, but it's really important in computer system. The reason behind that is you also need to make sure when you have distributed system where you have multiple servers connected to each other, you have consistent view of your data. So if you have questions like related to this or questions related to anything in the class during the break, come back and let me know. So let's meet at 12:55. Let's do a quick break, like 8 minutes, and we'll be back. All right. All right, let's get back. Okay, so let's put everything together, assuming this. Here's the assumption. We have a shared memory model, two level of caches, private L1 and the shared L2. There are two processors that share address X and Y. There's a load from the processor A, load from X, store to Y. Processor B, store to X, load to Y. All right. Any questions so far? A, load from X, store to Y. B, store to X, load to Y. Let's call this operation M, N, O, and P. M, N, O, P. What are the possible ordering, assuming the memory consistency model, the strong consistency model? What are my possible ordering? You have M, N, O, and P. How many? Actually, the first question, how many possible ordering that you can have? All right. Come on, let's do some math. 24, yes. How do you get 24? You have M, N, O, and P, right? You have 4 items. The possible way you can commute these 4 items, 4 factorial, is 24. The second question. Okay. Anything that's not clear here so far? M, O, P. If you go back one more, where are the store? Store is N and O, right? So if you have to put memory fence, what are the ordering between here that you have to be really, really careful about? What are the ordering of which of these operations you have to be careful about? If N and O are stored, M and P are low. Actually, M should happen before N, or should happen before P, right? Why is this the case? Why does M should happen before N and O should happen before P? Because M and N is from processor one, this is from processor two, right? M and N is from processor one, O and P is from processor two. Both processor is one Neumann. It's sequentially done. It means that if you have a load to X, store to Y, you should have this. You should see that order. It should be M before N, and then it should be O before P. So, is it really 24? If you know now that M should happen before N and O should happen before P. Nope, yeah, you are correct. So it's not 24 anymore. Why? It's 4 factorial over what? The possibility to sort this around and the possibility to sort this around, right? So it's 2 factorial here. So that's 6. If I do the math correctly, that should be 6. There are 6 ways you can do this. My first question is, I guess question 1A. Is this operation legit? I see M, O, N, P. Is this okay or is it not okay? This is okay. Why? We just know that M should happen before N, O should happen before P. Question 1B. What about this? O, M, N, P. M happen before N, O happen before P. This is also okay. Question 1C. What about P, O, M, N? You see that M happen before N. Yes, that's okay. P should not happen before O, so this is not okay. Any questions so far about this? Any questions so far about this particular example? Right? So assuming that somehow you're on the same page, if you have a question, definitely say something. Right? Say something so I can pause and I can ask you what are the things that I can explain to help you understand this concept. But basically, you should have some certain amount of ordering within the same processor. It's von Neumann, the way it should see that sequence. Question 2. Switch back to memory coherency. So you have a cache block. X is mapped to M. Y is mapped to cache block N. So those are two totally different cache blocks. My question when I said what does a cache block looks like, right? I really means what is the consistency state if I have first load to X from A and then store to Y from A and then store to X from B and then load to Y from B. Let's pick one order. Let's say that, okay, this happened first, followed by this second, third, and fourth. You first do a store to X from B. You have processor 1 cache for X. And for Y, processor 2 cache from X. And from Y, for Y, this is coherency state. And let's assume in the beginning, everything is invalid. Right? Invalid, 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 invalid. What is the first operation that I see? And who does that? Store to X from B. This is B, this is A. B store to X. So what do I do here? What is changed? What has to change? It's store to X, right? Originally it is invalid. If I have a store to an invalid cache block, what do I change to? Okay, so let me ask the first question. If I have this, store to X from B, who owns the cache block? Who will have the correct value of my cache block if I have to do store to X from B? Will it be A or will it be B? Or should I ask the question again if it sounds confusing? So if I have a write to X coming from processor 2, what will happen is the processor 2 cache will be the only location that has the correct data. So you will change to the modified state. Modified state means I did a write to this cache block. Yeah, I did a write to this cache block. Everyone else see that modified state. See that write change to invalidate. Everything is already in the invalidate state, so that's fine. The next operation is load to X from A. Load to X from A. What has to happen? This is the most updated copy of my data, right? This X is X prime. This is the most updated copy. This is old. Right? So you first need to flush. This is flush to the L2. Followed by, this is invalid, right? Invalid. It means that I need to go get data from my L2. It means that these data will move here saying, hey, this is the most updated copy of the data. X new here, and this changed to share. Why is it changing to share? Because now I have the most updated copy of the data, and the processor 2 also has another copy of the data that's most updated. So both of them will be in the share state. Any questions so far? So we are done with first and the second operation. Any questions so far? All right, let's do the third operation. Load to Y from B. Load to Y from B. We're done with X, so we're done with this, we're done with this. Now it's just the matter of how to deal with Y. So this load to Y from B, so you're looking at processor 2. We just need to get the data to Y. If I'm reading the data and I know I'm the only one who has the data, I will become the exclusive state. I have the data is clean, everyone can access the same data in the memory, but I will have the only copy of the data. Any questions so far? The next operation is store to Y from A. Y say, hey, I want to write my version of Y to the memory. When I do this, it means that I modify the data. Everyone else that sees this modification will say, hey, I don't have the most updated copy of the data anymore. I have to invalidate my cache block. That's it. Any question here? Any question here? Assuming that you haven't phased out and give up on listening to me talking. All right, so thank you so much. So let's do the last example. Same thing, but now it's the same cache block. Well, M, where basically this is, I'll just call it M. Processor 1, processor 2, M. You have load from X by processor 1, and then store to X from processor 1. Even though it's a different word, they can be on the same cache block because one word is depending on whether it's 32-bit or 64-bit. It can be 4 bytes or 8 bytes. One cache block is 64 bytes. So these two loads from X and from Y can be on the same cache block. And just something to mention. Store from store to y by p2 and then load from y by p2. And let's this time assume the order is this: 1, 2, 3, and 4. All right, so I first load. Originally, everything is invalid. I first load this data into P1, so I'm gonna change from invalid to exclusive because I am the only one who has the data. This is the updated data, let's call it M prime. The second operation is store to y by P2. I store, it means that I now have the most updated copy of the data, but it just happened my data is modified. This C modify, say, oh, okay, my data is not updated anymore. I will change myself to invalidated. This M double prime is a different version of the data. The third operation, store to X from P1. What will happen? M double prime is not the most updated version anymore. I have this M triple prime. This is invalid because I don't have the correct version of the data. And this is P2 say, I want to load Y. It's the same cache block. So you first flush. This flush, the data gets here. M double prime changed to M triple prime, which is the same data. Because there are now two owners of this data, you will then have to be in a shared state. And that's it. Basically, if you follow this protocol, it's basically really just follow the protocol. If I'm storing something, I should be in the modified state. Everyone should be invalidated. If I'm loading something, it's either share or exclusive, depending on the situation where that updated copy of your data are. And as you can see here, there's X and Y, right? It's the same operation as the first question. You have memory consistency comes into play. You need to make sure processor A see the load from X, then store to Y. It means that these operation have to happen before these operation. And these operation has to happen before these operation. That's where memory consistency comes into play. So if you think about that, right? If you think about it, when you have multiple processors with multiple caches, they all play its part, right? You can bring in the virtual memory, the caching, right? Everything comes into play. The reason why I don't mention virtual memory and caching is they are totally orthogonal in the sense that, well, each time you load the data here, it has to be properly cached. It has to be properly indexed by physical virtual address and tagged by the physical address. Right? So when you need the physical address, you do translation. Like usual, it has nothing to do with the fact that you have multiple processors, you still have to do translation like usual. Any questions so far? Because this is the conclusion of the, I guess, required material for the class. That's it, guys. We are done with the ComArch for MUIC. Okay, so we have 3 more lectures. I want to list out what's coming next, right? Assignment 3 extra credit part, which is the programming part, is already posted a while ago. We have the sample code. We have the starter code, which is actually, surprise, solution to assignment 1 and 2. So if you don't know how to do assignment 1 and 2, check the code out because that's how you can implement it. I know it might be, well, a little bit too late to finish up assignment 1 and 2, but it's still worth it for your learning experience to see, hey, this is how you can program to get things done, to get the pipelining done, to get to the part where you can have a functioning code. We have a reference simulator this time that you can compare Basically, if you implement your code, you should see the same result as a reference simulator. Then everything here is extra credit. It's worth the same as one assignment. So if you did not do any of assignment 1 and 2, definitely recommend to take a look into this. Definitely take a look into this. The written part is designed to take only 1 week, so it should not be heavily burden you too much, and is a good material for your exam. It will cover everything up to today material. It means that it might cover the before midterm part. You have until a day before the final exam to submit this. The reason why I give you more than 1 week is, well, I want to make sure this is also a possible study material for your final. And if you cannot do any parts here, we will actually go over some of these questions. Not giving you the answer, but I'll tell you how to work through the question. So you know how to actually do these in a more theoretical sense. The sample code, the starter code that I'm giving you for assignment 3 will show you how this can be done in more like a practical sense, right? But how do you build a simulator? What else? Some of you here show interest in quantum computing, so I'm gonna talk about quantum computing 101. This is probably next week. Uh, we'll talk about accelerators and tensor processing unit. This is actually on Wednesday. So Wednesday we'll talk about, okay, what are the rest that we can do as an architect, right? We don't just design general purpose computer like a CPU or a GPU. We also design really application specific accelerators. Basically, this is a special piece of hardware that's designed to do only specific tasks. It can't do the rest. How many of you heard about the new chip from Apple? Well, I might have asked that before. But it also that chip consists, that SoC consists of multiple accelerators on the package. We'll talk about why are they there? Why are they good? Why are they really delivering really high performance? This is a question back from the poll that we have in the first class, right? How to read the hardware specification. I'm probably will squeeze it in on Wednesday. Basically, when you buy DRAM, when you buy SSD, what does it mean? How many of you buy an SSD and see things like DLC, MLC, TLC? Anyone seen those before? So if you look carefully in SSD spec, these days you either will see this or QLC, I guess quad level cell. It means that one cells will represent not just 0 and 1, but multiple bits. And the higher this, the worse it would, the less reliable they'll get, right? So I'll tell you what they are and why. Why do SSD manufacturer have to do MLC? Right? MLC stands for multi-level cell. We'll also do a review. So this is going to be the next Wednesday. Next Wednesday we will review and cover what we covered so far. We'll work through homework 3, but the homework 3 part will be student driven. You come at least read the homework. I will answer the question. I will not solve the problem. You come with questions. I'll walk you through how to solve the questions, and I'll walk you through basically how to get to the answer. All right. So is that a handshake from like basically that's a policy. And that's it for today's class. So I'll cover quantum computing. I'll cover accelerators. I'll cover how to read hardware specs. I'll cover the review. Anything else that you want me to cover? I think one more thing I kind of want to cover is this like anyone heard about the Tesla self-driving car chip? So there's also things like specific accelerators for self-driving car. I'll talk about that as well. Anything else that you want to know beyond the scope of uh, the first poll that I have, that now that you learn all the necessary fundamental topics in architecture, anything else that you want to know besides these three bullet points? And please feel free to say anything. These are not going to be on your exam. Right? I just want to see, okay, we have time. So if you're curious about certain topics, let's do that discussion. Okay, so before it becomes like a really awkward silence, if you have any topics that you want to learn, feel free to like PM me, email me, contact me in any shape or form. Just let me know. Okay, I've seen this before. Can you explain it in the next class? I'll be happy to. Right? I'll be happy to explain it as long as I understand how this works. If there are like really topic outside of my expertise, I might refer to how would you learn more about it. But if I know what it is, I'll definitely cover that. All right. So that's it for today's class. Let me finish the recording here.